In this video, we are going to continue the final part of our series looking at the dielectric properties of materials. In this video, we're going to be having a look at a model which is able to simulate the response of an electric field which oscillates in time. Now, this is quite a common simulation for many things that occur within real life, because many times you'll be dealing with an electric field that actually constantly switches back and forth, a bit like a kind of AC circuit. And when you have this electric field that constantly oscillates, you actually get some really interesting properties emerging from the material. And in this video, we're going to come up with a model, a microscopic model, which is able to predict what the response of this material is within certain mediums. And just a disclaimer, we're going to be using a lot of the content that we've covered in the last two videos. So this includes the video about dielectrics and polarization, and also some of the concepts regarding polarisability and the Clausius-Mosotty relationship. So if you guys haven't seen those two videos, check them out here. So let's get into it. So in the last video, we introduced the idea of polarisability, and we said that the polarisability alpha right here is the constant of proportionality between the dipole moment, lowercase p, and the electric field. But we also said that this was the local electric field, because of course this wasn't the same as the electric field that was applied to the whole material, because the dipoles would produce a electric field that would kind of act as a kind of response to the electric field applied. So when we have this system, we have a system full of dipoles, which is our dielectric material. And we said that when we applied an electric field right here, there was actually a whole bunch of electric fields that were produced by the dipoles due to the fact that they have a positive and negative charge that sort of act to kind of counteract this electric field right here. And this is what we said was the dielectric response of a material. And we described this using the polarization capital P right here, which we defined as the number of dipoles per unit volume, capital N, multiplied by the dipole moment right here. And this is the macroscopic polarization. And experimentally, you find that this polarization P is proportional to the electric field, like the external electric field that is applied to the whole dielectric. And it's actually related using this formula epsilon naught multiplied by the susceptibility, the electric susceptibility this is, multiplied by the electric field. And in order to relate the polarizability, which is of course on a microscopic scale, to the electron susceptibility and also relative permittivity at that, then we derived the Clausius-Mosotty relationship, which basically said that the relative permittivity, epsilon r minus 1 divided by epsilon r plus 2, is equal to n alpha divided by 3 epsilon 0 right here. So this relates the relative permittivity, or the susceptibility, because of course the susceptibility is simply the relative permittivity minus 1, to the polarizability right here. And we also said, which is quite important to this, is that the dipole moment P is approximately equal to n alpha times the external electric field if n is sufficiently small. So physically what this would mean is if the dipoles were spaced apart, then that would simply mean that the fields produced by the dipoles would not really have much of an effect on their kind of local vicinity, because they're also kind of spaced apart. And therefore you can just simply substitute in P equals n times big P, polarization, and use, the P equals alpha E to simply get that right here. But remember, we can only apply that in the sort of dilute limit of the dipole. So that's all well and good. So what are we going to consider in this video? Well, we are going to go back to thinking about the case where we have a bunch of atoms within our dielectric, and these atoms are all initially when there's no electric field applied, these atoms do not possess any kind of dipole moment. So what this would mean in practice is that the nuclei of all these atoms right here would all be at the center of the atoms. So if they're at the center of the atoms, then there would just not be any dipole moment right here. So they would be symmetrical. So we're going to consider atoms that are a bit like this. But of course, when we apply our electric field, so say we apply our electric field in this direction right here, of course, the electric field lines run from positive to negative. So positive end would be this side, negative end would be this side. The electron cloud would be distorted towards the positive side, and the nucleus would be distorted towards the negative side. So we'd actually end up with all of our atoms kind of looking a little bit like this. So we'd have this kind of off-center position of the nucleus with respect to the electron cloud right here, because of course the nucleus, which is positively charged, would be attracted to the negative side of the electric field, and vice versa for the electron cloud right here. And this only happens when the electric field is turned on. As soon as the electric field is turned off, then you have this situation right here, where of course there is no dipole moment for any of the atoms, but in this situation clearly there is a dipole moment, which runs of course from negative to positive, and this kind of distance right here is kind of what defines the dipole moment, and this is the kind of displacement between where the nucleus is now and where the center of the electron cloud is. Now we can actually calculate what the electric field would be at a point within a kind of cloud of electrons using Gauss's law. And so what we're going to do is we are going to apply Gauss's law in order to determine the electric field felt by sort of a test charge, which in this case would actually be our nucleus, a test sort of small test positive charge in the midst of an electron cloud. And so let's go ahead and redraw our kind of system right here. So here we have our kind of negative cloud of electrons. So this is of course a distribution of charge. And let's go ahead and call this radius just capital R right here. So there's a giant cloud of electrons that's kind of a radius R. This could be the Bohr radius or something. And of course, our kind of positive test charge is off the center right here. Of course, if it was in the center, then it would not experience any electric field because of course it would just cancel out on each side. But because it's not in the center, it's going to experience an electric field, which is trying to pull it back into the center. So here is our positive charge, and here is kind of the center of our negative charge. And of course, opposites attract, and therefore there's going to be a force caused by the electric field that could kind of be considered to be originating from here, pulling it back towards the center, pulling it back towards this position right here. So what is that electric field? Well, if we apply Gauss's law tells us that we can construct a sphere around the center of our cloud of charge, and we can say that the electric field that goes through the surface of the sphere, E dot ds, is equal to the charge that's enclosed within the sphere. And remember, this is not the sphere of our electron cloud, this is just the sphere of our Gaussian surface right here. Very important to make that distinction. Divided by the permittivity of free space. But we also said we could express the charge in terms of a continuous charge distribution given by the integral of the charge density, which is the charge per unit volume, all integrated over the entire volume. And remember, this volume is not the volume of this kind of electron cloud right here. This is the volume of the Gaussian sphere that I've constructed right here. So, because of course, the only charge that contributes to this electric field is the charge that's enclosed within. This is Gauss's law. Let's go ahead and see if we can try and evaluate this. So, of course, E dot ds, well, ds is of course just the surface of this sphere. And this is kind of like the sphere in which you can evaluate the electric field at. So we normally give this sphere lowercase r. So because, of course, for symmetry reasons, there is only a radial component to this, because, of course, it's a spherically symmetric system, then we're simply just going to get that the R component of the electric field multiplied by the surface area of the sphere right here, this small little sphere. And what are we going to get on the right-hand side? Well, we're going to get our 1 divided by epsilon naught. And similarly for the charge density, we're assuming a constant uniform charge density of this electron cloud. I mean, technically this isn't quite accurate because, of course, you are actually more likely to find an electron within certain parts of the atom than others, as is what quantum mechanics tells us. But for now, we're just going to kind of pretend that's not a thing. And so we're just going to go ahead and take this row out the front of the integral and just simply multiply this by the volume of this sphere. 4/3 pi r cubed. And of course, remember, this is the small sphere because we're only talking about the charge that's enclosed within the sphere. So as you can see, a lot of stuff is going to cancel. The 4 pi's on both sides cancel. This r squared is going to cancel with 2 of the r's over here, so you're just going to get r. So all that's left is that the electric field is simply equal to rho, the charge density, multiplied by r, divided by 3 epsilon naught. And that's quite an interesting result because, of course, this kind of contrasts quite radically with the result of a point charge being proportional to 1 divided by r squared, this kind of inverse square law that we're all familiar with. And of course, this is because we're inside a charge distribution. We're evaluating the electric field within a charge distribution. So obviously, because there's charge kind of everywhere all around us, then we're not going to expect it to be the same as it is for a vacuum. And so interestingly, you find that the further away from the center you get of this electron cloud, you actually find that the electric field value increases. And it will increase right until it gets to the edge of the atom right here, at which point it will then behave much like a point charge. So we have a system where the electric field is proportional to the distance. So the electric field that's experienced by this nucleus right here is actually going to increase proportional to how far it is away from the center of the atom. Now, this is actually very similar to another system that we actually study quite a lot in physics. And whenever you see something that is a sort of force term, which electric field is just essentially the force, it's the force per unit charge, it's proportional to the distance, then this is actually very similar to our mass on a spring system right here, where when we displace this mass on the spring away from the equilibrium position, we actually find that there's a force, a restoring force, that kind of pulls it back towards the equilibrium position. And of course, this is directly proportional, which is what basically Hooke's law says. So this is essentially the same as Hooke's law. It's saying that a force is proportional to the distance. So when we apply our electric field to our atom in order to create a dipole moment, it's almost the same as basically pulling a mass away from the equilibrium position on a spring system. There is a force that's trying to pull it back towards the center. And this is really, really useful because whenever we have a system like this, we can actually write out a differential equation which describes this motion very, very nicely. So that's what we're going to do. We're going to go ahead and write out a differential equation, which is going to be very similar to the differential equations that hopefully you guys would have seen in the simple harmonic motion parts of the course. As you can probably tell, it's probably going to oscillate very similarly to how a mass oscillates on the end of a spring. Now, we're actually more interested in modeling the electrons sort of oscillating, which is actually kind of what's going to give us our kind of model of the material in response to an electric field that's applied externally. Because, of course, the electrons are actually going to be doing all of the sort of things like the conduction and giving us rise to all of the properties. So actually what we want to do is, rather than model the nucleus, we actually want to model what's going on with these electrons. Now, This is maybe a little bit less counterintuitive to think of the electrons as being kind of the mass, but Newton's third law rather nicely tells us that because every action has an equal and opposite reaction, that basically means that the force experienced by the electrons, this electron cloud, I should say, by the nucleus, is actually the very same as the one that we've just been considering, which is, of course, the force acting on the positive charge or the positively charged nucleus from the electrons. All we have to do is we have to essentially reverse the sign. So the force from the nucleus on the electrons, which is going to be the first term in our equation of motion, is simply equal to the charge, which is minus E for an electron, multiplied by the electric field that we apply, the external electric field. However, as we've just shown, this electric field, which is applied, is not going to be the only force acting on our system right here. And of course, there was this kind of restoring force that we've just kind of calculated, which is going to be acting in the opposite direction to the electric field. So we're going to have a restoring force, which we normally give minus kx for a spring. So of course, k is the spring constant and x is the displacement right here. But we can actually also write this as minus m omega squared times x right here. Now, this is all from simple harmonic motion. Omega right here is the resonant frequency of a mass on the spring and is normally given by the formula of the square root of k divided by m right here. And this kind of comes out when you solve the differential equation of simple harmonic motion right here. Now I'm actually going to just call this omega naught right here because we're actually going to have a couple of different frequencies that we're going to be considering. So omega naught is just the resonant frequency of our kind of mass on a spring system, which is kind of our atom, which we're modeling as a mass on a spring. So therefore the restoring force is simply equal to m omega naught squared multiplied by x. That's our restoring force, that's our electric force. But there is actually going to be one more force, and this force is due to damping, which goes on within our system. And of course, whenever you have a system that's oscillating, it's very rarely going to keep on oscillating forever and ever and ever. There's going to be a time where the system just gradually kind of returns to equilibrium, of course. It will never quite get there. That is essentially what's going to be happening. And this damping force, normally we say that any damping force is proportional to the velocity of our moving particles. So basically, the faster our electron cloud moves with respect to the positively charged nucleus, then the more restoring force there will be. Now, it was actually a little bit more complicated than it would seem, and the damping is actually due to scatterings that are going on within the material. And we're actually going to be getting into what the damping actually physically is a little bit later, but suffice to say for now, we are just going to introduce this term, which is proportional to the velocity. And normally when we talk about a damping force, we add a proportionality constant of minus b in front of it. Of course, it's minus sign, because of course it acts in the opposite direction to, where it's meant to be going. It acts to oppose the change that causes it. But we can also express this right here as, rather than b, we're actually going to express b in terms of a constant called gamma right here. So what I'm going to define is that b is equal to gamma multiplied by m, the mass of our electron cloud right here. And this actually kind of pops out when you're solving the equation for simple harmonic motion. You actually get this kind of, it's much more handy to think of it in terms of gamma times m, rather than just the damping constant b right here. So our damping force is going to be equal to minus m gamma v. However, we can express the velocity v as being equal to the first derivative of the displacement, which we normally just give the symbol x dot. This dot right here just indicates that you're taking the first time derivative of the displacement right here. So those are all our forces that are acting on our system, which means that we can now write our net force that is acting on the electron cloud. So we have our electric force, which is given by minus EE. But of course, we're going to have our restoring force, which is minus m omega naught times x right here. And we're also going to have our damping force, which is m gamma x dot right here. And whenever we have a net force, we can always equate this to mass times acceleration. But of course, acceleration is the second derivative of displacement. So to represent that, we're just going to write two dots on our x right here. And so this basically means the second derivative of displacement with respect to time. So rearranging this equation, we are going to get mx double dot plus m omega naught squared x plus m gamma x dot is equal to minus e right here. So this is kind of, we're just getting all of the terms with x on one hand side of the equation and all the terms without x on this other side. And this is going to be very useful for the method which I'm about to introduce, which is going to solve this differential equation right here. So this is all great, but what did I say at the start of the video? I said that our electric field, instead of just being this kind of electric field that just we turn on and just kind of stays there, this electric field is actually going to be oscillating with time. And what do I mean by this? Well, I mean that it's going to sort of make this pattern right here. So it's going to make a sinusoidal pattern over time. So at one time, it's going to be sort of facing in this direction right here. And then a certain time later, it's going to be facing the opposite direction right here. So it's going to be oscillating over time. And the way in which we mathematically represent that is that you say that the electric field right here as a function of time is equal to the amplitude, which is sort of this distance right here, or this electric field value right here, multiplied by cosine of omega t. So this is how we would normally write it, or equally you could in fact write this is equal to sine of omega t. And in fact, I've actually drawn a sine function right here rather than a cosine function. But instead of writing this in terms of cos and sine, we can actually use Euler's theorem, Euler's identity, which says that e to the ix is equal to cos x plus I sine x, to actually write this right here in terms of an exponential right here. Now, it doesn't really matter whether we use cos or sine. It actually kind of gives us the same physics. All that really means is there's a phase shift. But essentially, we can just, instead of writing E naught times either cos or sine, we can write E naught multiplied by e to the I omega t. And all I'm going to now do is, instead of writing e to the plus I omega t, I'm actually going to write this as e to the minus I omega t right here. Now, this might seem a little bit weird, like why am I just adding a minus sign? Well, physically, this doesn't really change what we're kind of representing right here. Like, we're still going to end up with an electric field that oscillates in time sinusoidally, which is basically all the physics. I mean, it's just like either swapping out cos for sine. It doesn't really change any of the physics. It just sort of just affects the phase in that case. But in this case, it just basically means we're oscillating in the clockwise direction rather than the anti-clockwise direction. So now we're just going to go ahead and plug this term back into our differential equation right here. So we're going to get mx double dot plus m omega naught squared x plus m gamma x dot is equal to minus E times our electric field. Remember, this E is the charge of the electron right here, and this, of course, is just the exponential. So we're going to get E naught multiplied by e to the minus I omega t right here. So we have our second order differential equation right here, which I'm just going to highlight. And There are many ways to solve this equation right here. Maybe you guys are familiar with certain methods. I'm actually going to be employing a method that is a little bit different to normal, and I'm going to be Fourier transforming this equation right here. And I actually think this is one of the most easy ways to solve a second order differential equation when you have something that's kind of x double dot, x dot, and x right here. I actually think Fourier transforming is a really easy and nice method which you can use to solve it. So that's what I'm going to do. I'm going to Fourier transform both sides of this equation. Now, if you guys are not familiar with Fourier transforms, then it may be worth going and have a look at the various math lectures which kind of cover this sort of stuff, because it's probably one of these things that will either get covered in sort of first year of university or second year of university. So, and it's quite an important physics concept, so I'd imagine most physics courses would cover things such as Fourier transforming. But the thing we're actually going to be making use of is actually a really useful Fourier transform identity. It's actually a property, a really nice property that comes out of Fourier transforming a function. So when I take the Fourier transform of x right here, so this is our sort of x, which is a function of time, and we're trying to find the solution for x as a function of time right here. That's the point of solving a differential equation. When I Fourier transform this, I am going to get this kind of inverse function, which is a function of the frequency omega. Now, here is an important point. This omega right here is not the same as this resonant frequency omega right here. This omega is in fact at the moment just a mathematical variable which we haven't assigned any sort of physical significance yet. So this is just any frequency right here. And I should also point out that this omega right here is actually the driving frequency of our electric field. I should have maybe made that a little bit clear earlier on. But this omega is how fast we're driving the frequency. But this omega right here is just a mathematical variable. So there's nothing much to worry about with this omega as of right now. Later on, we're going to ascribe physical significance to this omega. So that's what happens when I Fourier transform just a function of time. I get this inverse function of frequency. But the thing that's really useful is if I Fourier transform the derivative of x with respect to time, I actually get, when I do all the mathematical calculations, and you can prove this, I times omega times the Fourier transform, just the normal Fourier transform of x right here. And this is a really useful property, and this is actually the property that enables us to solve this differential equation so easily, because of course we just simply get various factors of I omega out when we take a Fourier transform of our function right here. And so similarly, when we take the second derivative of x with respect to time, then we're just going to bring out another factor of I omega out the front. So when we multiply I omega times I omega, we're just going to get minus omega squared times the Fourier transform. So it's actually a really nice property of derivatives of functions. In Fourier space, you're just kind of multiplying it by factors of I omega every time you differentiate. So that's really, really useful. So we can just go ahead and plug all of these in to the left-hand side of our equation right here. So remember, I've taken the Fourier transform of this entire equation. We're going to get m times the Fourier transform of x double dot, which is this right here, is simply equal to minus omega squared times the Fourier transform of x right here, plus this term right here, so m omega naught squared. Well, m omega naught squared is just a constant, and when we Fourier transform x, we're using this right here, which is of course just the Fourier transform of x, which is a function of omega. And finally, our damping term, so m gamma is just a constant, but we are going to use this identity right here, which tells us that the Fourier transform of the first derivative is simply equal to I omega times the Fourier transform of the original function. So we're going to get a factor of I omega right here times x. And this is all equal to minus E times the electric field amplitude. And remember, I've Fourier transformed this whole equation. So for now, I'm just going to write the Fourier transform of e to the minus I omega t, omega d times t, right here, where omega d is our driving frequency. So this is looking good. One thing we can do is, because we have mass all common to every term on here, I could have actually done this a little bit sooner, but I'm actually just going to divide both sides of this equation by mass, which basically means removing the mass terms and then just kind of putting it underneath here, right here. So this is kind of just a little bit neater, a little bit more compact, which is fine. So now all we have to do is we need to Fourier transform this right here. Now this right here is actually a tricky Fourier transform to evaluate if you're using the definition of Fourier transform, but you can kind of get an intuitive understanding of what the Fourier transform of this function is. Remember, we have a oscillating wave. Of course, you know, this is a complex wave, but I'm only showing the real part essentially. But this wave is just of one frequency, omega d right here. And remember the point of Fourier transforms. When we Fourier transform anything, what we're trying to do is we're trying to pick out the specific frequencies of any wave right here. That's basically what a Fourier transform is. We take in a wave and then we figure out what are those frequencies. Now, when you just have a simple sine function like this, or in this case, a complex exponential function, there is just one frequency. This wave is only of one frequency. If we had something more complicated like this, then of course there would be a Fourier spectrum. But in this case, we've only got one frequency right here. So how does that translate mathematically? Well, there is a thing in mathematics which basically only is sort of on for one specific frequency, but is not on for any other frequencies. And so you guys may have cottoned on to what this actually is mathematically, and yep, you guessed it, this is the delta function, the Dirac delta function. And the whole point of the Dirac delta function is that it's only kind of on, it's only activated at one very specific value right here. So if I have the Dirac function of, say, x minus 3, when I plot this out on a graph, what I'll actually find is that there will be no value of the delta function for any value other than 3, where this delta function will spike and then it will go to infinity, and then it will immediately drop down for all other values and then just kind of continue on as normal. It's a weird function for sure, but this is basically what we're saying. We have this kind of one frequency, which therefore corresponds to just one spike in our Fourier spectrum. So this is what the Fourier transform is. The Fourier transform of a wave with a single frequency is just this delta function right here. So let's go ahead and write out our entire equation. So we've got, and that is equal to E naught divided by m multiplied by this delta function. So what's this delta function going to look like? Well, this delta function, of course, we said was going to spike at this one very particular frequency, which is our driving frequency right here. So we're going to have omega plus omega d right here. And actually, due to the way that the Fourier transform is defined, we're actually going to have to multiply by a factor of root 2 pi. Now, this is actually just because when we take a Fourier transform, we actually are transforming between time and angular frequency, where of course angular frequency is just linear frequency multiplied by 2 pi. And there's a convention on how you distribute the 2 pi that we're using the physics convention, where you simply put the 1 over root 2 pi on both transform integrals. So that is what we have. This is our Fourier transformed equation of motion right here. And what we're going to now do is we can now fairly easily just rearrange for the x right here. It's not the actual x that we really want, but it is just the x that we are kind of after. So If we rearrange this for x as a function of omega, we get minus root 2 pi e naught multiplied by this delta function of omega plus omega d, all divided by the mass, and we're going to get a set of brackets right here, minus omega squared plus I gamma omega plus omega naught squared. Now we have our x as a function of everything, but of course we're still in the frequency domain, and we actually want to get back into the time domain because this was what is going to give us our equation of motion. So how do we do that? Well, if we recall the definition for how to perform the inverse Fourier transform, this is given by 1 over square root of 2 pi times the integral between minus infinity and infinity multiplied by our function in the frequency space times e to the plus I omega t. Now there is a bit of a convention about this. The convention that I'm using is that when performing the inverse Fourier transform, you multiply by e to the plus I omega t, and when you perform the direct Fourier transform, then you use e to the minus I omega t. So let's go ahead and plug in our x right here, and we're going to multiply that by e to the I omega t. Remember, this omega is, of course, just the mathematical variable at this point. There is no physical significance. This is not the same as the driving frequency or the resonant frequency right here. So we have rather a nasty looking integral right here. But as we can see, we can make a few simplifications. This root 2 pi will cancel with this root 2 pi. Of course, that's actually why we added the 2 pi, because of course we needed it to cancel. And there's going to be a minus sign out the front. We're going to get minus e naught divided by m multiplied by the integral of this Dirac function divided by the denominator right here. So we're going to get minus omega squared plus I gamma omega plus omega naught squared. And we're going to get an e to the I omega t d omega. So we just brought the constants out the front. Now, this might look like an absolute nightmare, but this delta function is going to help us out a lot, because this delta function has a really, really useful property, which actually makes it so that we don't have to do any integration whatsoever, really. What this property is, and I did go through this in my video about the delta function, is that this delta function is basically a sift for the frequency which it actually wants, which is actually corresponding to. Or to be more precise, this is the frequency at which the delta function diverges to infinity, or where it spikes right here. And it only spikes at this one value, which is, in our case, minus omega d, because when we have Dirac of minus omega d plus omega d, we get Dirac of 0, which is, of course, an infinite spike. That's how it's defined. So this means that when we do our integration, which is basically going along this entire omega axis, this delta function is going to be 0 for all other values other than minus omega d. So there's actually no integration to be done whatsoever. All we have to do is we have to substitute into this expression right here minus omega d, because of course that is the frequency at which the Dirac function peaks. So this we can just rewrite as minus e naught divided by m times e to the I omega d t, which is our driving frequency. And now we just have to substitute in the driving frequency into the denominator, which is minus omega d squared plus I gamma omega d plus omega naught squared right here. So there we go, we pretty much have it. I mean, we can tidy it up a little bit. We can just kind of get rid of this minus sign and change all the signs on the denominator right here. So this will be a minus and this will be a minus right here. But essentially that is our equation of motion. This is our displacement of our electron cloud as a function of time right here. We have no things. It's actually a function of a couple of different frequencies. The driving frequency and the resonant frequency of our kind of spring in inverted quotes. But this is essentially what we have right here. So this is great. This is our displacement. However, we can easily relate our displacement x right here to the dipole moment P right here, because of course we said that P is simply equal to the charge times the displacement. And of course, our displacement of our electron cloud from the center is actually what's giving rise to our dipole moment to begin with. So this x right here, of course, corresponds directly to this kind of d right here. And of course, because it's minus omega d, we actually are just going to be substituting in minus omega d. So these signs are actually all going to change. My bad. So P is simply equal to the charge, which is of course minus E for an electron, times x. And so this is now going to be a function of time. So we're just going to be multiplying this all by minus E. So we're going to get minus E squared, E naught divided by m, times e to the minus I omega t, with just everything on the bottom right here. And what I'm going to now do is I'm just going to remove the minus sign and then change all of these signs on the denominator right here. So this is our dipole moment as a function of time. But what did we say the relationship between the dipole moment and the electric field is? We said it was P is simply equal to the polarizability multiplied by E right here. But what did we say our electric field was? Well, our electric field, E, was equal to E naught times e to the minus I omega d t right here, which is of course what popped out when we did our integration earlier, which is great. So we can actually write this as the dipole moment induced is equal to E squared divided by m times this factor right here, 1 over omega naught squared minus I gamma omega d minus omega d squared, multiplied by the electric field. So, and now it should be fairly obvious that this term right here is the proportionality constant relating P and E, which is of course just alpha, the polarizability. And so we get the final result for the polarizability is equal to E squared over m times 1 divided by omega naught squared minus I gamma omega d minus omega d squared. And this is our final result. This is the polarizability of our atom as a function of the driving frequency right here. So we've derived a model which basically is going to predict how our dielectric changes in response to an oscillating external electric field, which is great. That's really, really good. That was kind of what we were after. So because that calculation took a very long time, I'm actually going to end this video off right here as part 1 of 2. This was the important calculation that we kind of needed to do in order to obtain the polarizability as a function of our kind of oscillation frequency, our driving frequency of our electric field. But now that we have this equation right here, what we can now do is we can apply this to various different scenarios in which we have a system of atoms, which of course can have a dipole moment in response to our externally applied electric field. So this could include anything like a gas, it could also include a solid, but we're also going to be really having a look at metals right here. So stay tuned for the next part in which we're going to be applying this model to all of those different scenarios. And we're actually going to be getting into some really interesting kind of properties of these materials right here. So see you guys then.